So in 11.3 we see that Mach number is another way to describe a very fast aircraft, a way to describe its speed. So versus kilometers per hour or miles per hour or meters per second, Mach number is a ratio. It's a ratio of how fast the aircraft is going compared to the speed of sound. So Mach 1, if there's an aircraft that's traveling Mach 1, that means that the aircraft is traveling at the speed of sound. That's what Mach 1 means. Okay? So whatever the speed of sound is, the aircraft is doing the same speed, and so that is, a ratio of 1/1. Right? Or let's say the speed of sound in air at this particular, altitude and temperature is 350 meters per second. I was frozen there, sorry. Meters per second, and the aircraft is doing 350 meters per second as well. So the Mach number is 1. You see that? So Mach 1.5 would be 1.5 times the speed of sound at that temperature. Pretty easy. Okay? So Mach 3, 3 times the speed of sound. Right? So we're talking almost 1,000 meters per second, that sort of thing. Pretty fast. Alright, so it's pretty simple. That's what Mach number is. Now, let's say we're given the speed of sound in kilometers per hour. Okay, so if we have the speed of sound, okay, just write this one out here. So let's say the speed of sound in a particular situation is 1,060 kilometers per hour. Okay, and the aircraft speed is 1,800 kilometers per hour. What's the Mach number? Oops. Okay, so just take a second to do that on your calculator. Okay, Mach number. Don't worry about sig figs. No, don't worry about sig figs. Right, so Mach number is the speed of the object divided by the speed of sound. So 1,800 kilometers per hour divided by 1,060 kilometers per hour, 1.69. Now, someone asked about sig figs. Okay, yeah, it would be 2 in this case, right? 2 sig figs would be the lowest number of sig figs in this. But anyways, 1.7, so 1.7. If you're wondering how many decimal places are sig figs, just go ahead and use sig fig rule. You never go wrong there. 1.7. Okay, so Mach 1.7. And again, that's just a simple ratio of the speed of the object to the speed of sound in air at that for that situation. So you might have a question like this where you have to do some unit conversion. So once again, just as you finish writing this out here, the speed of an aircraft, let's say, is 1,937 kilometers per hour. So it's traveling pretty fast. The speed of sound at these conditions that this aircraft is traveling at is 342 meters per second. So we have speed of the object in kilometers per hour and the speed of sound in meters per second. If you're asked to find the Mach number, you have to make sure that the units line up. Remember, that's always what you do. You can't do 1,937 divided by 342. You can't do that because the units aren't going to line up. That number you get is not going to be the Mach number. The units have to line up. So let's take a look at how we can convert these units. Do you remember how to do that? Best way would probably be unit analysis, right? So let's say 1937, that's kilometers per 1 hour. So to do this, to figure this out, you want to end up with meters per second, right? So I got to get rid of the kilometers. Let's do that first, km, and I want to express that in meters, right? So how many meters in a kilometer? 1,000 meters in 1 kilometer. So that's your first conversion factor. And we do that because kilometers and kilometers are gone, right? Okay, so the next one. Now I've got meters. See, right now I have meters per hour. Is that what I want? Nope, I want meters per second. So you might know this already by now. You can chunk this down into smaller pieces, but you might already know how many seconds are in an hour. You might have that at the top of your head. 3,600, right? 3,600. It's 60 seconds per minute times 60 minutes per hour. So if you know this already, I'm totally okay with you just throwing this conversion factor down there right now. That's totally fine. So we see that hours now are gone, and I'm left with, this is really good, meters and seconds. You see that? That's exactly what I want. So what you do is you go 1,937 times 1,000 divided by 3,600. And that's going to give you your value in meters per second. So just go ahead and take a second to figure that out. So 538.05, that's in meters per second. So now that we've got this in the proper unit right here. Now I can do a straight division. So Mach number equals 538.05 divided by 342. And this is going to be, there's no unit for Mach number, remember? Because the units divide out. Meters per second divided by meters per second, or whatever they are, they divide each other out. So there's really no unit. It's Mach 1 point whatever. So if we do that real quick, 1.57. Okay, so there's your Mach number, 1.57. You guys get that value as well? So just for interest, this is a YouTube link here on the side. If you guys watch this video later, you can look up the sonic boom or sound barrier compilations, I think it's called. But anyways, this is the link to the video that we just watched in class. All right, so as we move through here, transmission of sound waves, let's take some notes here on 11.4 in your textbook, page 354. So let's talk about how sound waves move and the transmission. We've mentioned that sound is a wave that moves through a medium. The way that sound moves is called the transmission of sounds. Trans means movement, okay? Transporting, right? Transmission means it's sort of how something moves through something else, the transmission, how it's transmitted. Consider a tuning fork. Now we've talked about tuning forks, seen the demonstrations. When the tines are hit, they vibrate, right? As they vibrate, they push the molecules of air closer together and then pull them farther apart. So it's kind of like this, you remember the slinky, the longitudinal wave, right? So that's what happens when sound waves are created. It's sort of a back and forth kind of push and pull in the air. What ends up happening is you have an area of high pressure and an area of low pressure. And we've talked about this already. You should know this already. You might even have these in your notes from a discussion we had before. But the area of high pressure is called a compression. The area of low pressure is the rarefaction. And you may have that written down already somewhere in your notes, but that's very key to what we're talking about here. And of course, the kind of wave that we're talking about is a longitudinal wave. Something to remember when we're talking about sound is that individual air molecules, they don't travel very far. If you think about this classroom right now, we've got 30 kids in this classroom here right now, and it's pretty packed, right? If we all got together shoulder to shoulder, right, and I pushed somebody on the very end of this big group, okay, with enough force that that person, kind of tumbles a little bit or stumbles and bumps into the next person, and then that person would bump into the next person, there would be a little bit of a domino effect, right? But if you consider a person that is in the middle, if that kind of comes to them, if that force comes to them, they would move a little bit and bump the next person, but then they would kind of stand back straight again, right? So the energy would transfer through the whole group, but each person would only, stumble just a slight, maybe 1 foot, right? Like just a very small amount. So each individual air molecule doesn't travel very far when sound is transmitted through the air. Now, also remember, let's see here, they vibrate forward into the compression and then back into the rarefaction. So we've seen in multiple videos how these air molecules sort of bump into each other and they kind of pile up, and then they kind of spring back into that area of less dense air molecules, right? So if they're piled together, they bump into each other, and then they kind of like stretch out apart, and they kind of are like this, right? So they bump into each other in a compression, and then stretch back into the rarefaction. Again, you guys, we've talked about this, so you guys might, this might be just a review, some of this already. But when we talk about wavelengths, right, in longitudinal waves, it's the distance between two compressions or two rarefactions. And that from our Slinky lab, you saw that, and yeah, just from other discussions in class. All right, so something new when we're talking about sound, okay, so compression, rarefaction, wavelength, something new is a term called pitch, all right, when we're talking about sound. The terms used to describe other waves are also used for sound waves. The word frequency, okay, which you know all about frequency, and it's down here in this frequency equation, right? But that is often substituted for pitch when referring to sound. So you guys have probably watched, some American Idol or The Voice or something like that, and you've heard people say, well, your performance was just a little bit pitchy. Okay, you ever heard that before, When they say you were a little bit pitchy, that means that you were off pitch at some points when you're singing the melody of the song. You weren't quite in tune with the music, right? You're a little bit pitchy. And that's exactly what they mean. They mean that the frequency of the sound that you were making when you were singing is not in line with the actual sound that it was supposed to make. So you're a little bit off in pitch. Okay? It happens to me all the time. Happens to all of us all the time. But pitch is the basically the note of sound. So each note has a frequency, and that's what we refer to when we say pitch. Do you guys know what the note A on the piano is? Everything, when we tune pianos and guitars, there's a standard frequency for the note A. Does anyone know what number that is? How many hertz the frequency for the note A? If any of you are guitar players or piano players and you've seen one of those little tuners, okay? When you turn it on, I don't know if you ever look closely at the screen, but next time you should. If you look closely at the screen, you'll see a frequency up in the right corner. And as a matter of fact, I think I have one. Just give me. Here is a tuner. Now I'm going to try and get this right up to the screen so you guys can see that. I'm not sure how this is going to work, but you see in the very corner, right by my finger, right there. I don't know if you can see that, but it says 440 hertz. And on every tuner like this, you'll see that number up there. And you can actually change that. I don't know why they have this here, but anyways, you could change it 442, 443. If this accidentally gets bumped right here and you're trying to tune a guitar or something like that, and you bump it up to a different frequency, you are going to be out of tune from the rest of the instruments. So 440 is the standard tuning, and that's based on the A note being 440 hertz exactly. So I'm gonna try this here. I'm gonna try and sing an A note. I don't even know where to start. But what I'm gonna do is I'm gonna watch up here for the note, right? So let's see. La. Okay, C sharp. Those of you musicians, is that higher than A or lower? A little bit higher. La 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 la. Oh, la. Okay, I can't go that low. Shoot. La. Well, there's an E. Anyways, I'm getting better. Although it's a fruitless exercise, I think. Anyway, so I was pretty close to A there. But you see how the pitch went down, and it actually showed a different letter right there. Let's try it one more time. La. There's D. There's D. La la. There's a C. I got pretty close to a C. Okay. All right. Let's cut this video here now. Beautiful. Okay. 11.5 in your textbook. These sections are really super small. So, 11.5 in your textbook talks about the intensity of sound. Now, intensity and frequency are different. They're not the same. When we're talking about the intensity of something, it's kind of like, something is louder or it's kind of ramped up. It's a little bit more in your face, right? Intensity. So frequency or pitch and wavelength and velocity are all measurable quantities of sound. So frequency is f, wavelength lambda, velocity v, all related in that equation. Typically, we measure the size of a wave by looking at its amplitude. Okay, so that should really be underlined there as well. We talk about the size of the wave by looking at its amplitude. But this doesn't work for longitudinal waves. So what sound is longitudinal. So we can't really look at amplitude. So how does this work? This doesn't work for longitudinal, which sound is, because the medium moves in the same direction as the wave. So, in this kind of a wave, we could easily calculate what the amplitude is. But in a longitudinal wave, right, something like this, it's kind of hard. Now, we could dissect this and figure out, hey, if this is that's the wavelength, okay, so we're going up, but right here, how do you know these compressions? How close are they? Or how do you know, right? So instead, we measure the size of the wave. So we measure the size of the wave by measuring how much energy it carries. How much energy it carries. Just a reminder, the parts that are underlined, you should be writing your notes, right? Okay, I've tried to shrink this down for you to just some basic highlights here. How much energy it carries. So this is the intensity, and it's measured in a pretty kind of a weird combined unit, watts per square meter. Watts per square meter. So you'll see this written like this in your textbook, and you should probably write this down, measured in watts per meter squared or per square meter. And this is what the unit looks like, capital W for watts. The range of human hearing goes from approximately 10 to the negative 12 watts per meter squared to 10 to the positive 4. This is such a wide range that scientists have come up with a more user-friendly scale called decibels. But now let me go back here. So when we're talking about the frequency of human hearing, like what frequencies we can hear, this is not talking about frequencies anymore. We're talking about intensity. So basically we're talking about loudness, right? It's how much pressure, okay? Notice that this is a unit for power here, watts. Okay? It's a unit for power. And this is a unit for area, right? Meters squared. So it's how much power basically is pushing on how much area. So if you have a lot of power in a small area, right, you're going to have a high intensity. So this intensity level of sound, not frequency, but intensity level, we measure in decibels. And some of you have heard of decibels before. The decibel scale was created by Bell Labs in 1928. It was named after Alexander Graham Bell, and is called the decibel to show that it was based on the powers of 10. So notice the deci part, okay, decibel. Okay? So this is a more user-friendly scale of measuring and of communicating intensity of sound. So the decibel. The scale assigns the lower threshold of human hearing a value of 0 decibels. So what this means is the quietest sound that a human person would be able to detect from in their eardrum, right? The lightest pressure, the quietest sound would be 0 dB. That's the threshold. So after 0 dB, you start registering, your brain starts saying, hey, I hear something. Now, for most of us, we can't hear things that are at 1 dB. Like, it's too quiet, right? But that's sort of the threshold of where things would start. So there's no negative decibels. So, in other words, this is the weakest sound, or the quietest sound that we can hear. And I'll just write quietest there too. You might want to add that. The quietest sound that we can hear. So this scale is also set up a little differently. It's set up like this. Every increase in 10 on the decibel scale is an increase in intensity of a power of 10. So this means that 10 decibels is 10 times more intense than 0. Let me just see this. This looks a little funny. 20 dB is 100 times more powerful. Yeah. So the power of 10. So let's, this 0 and 10 is a bit misleading. But 20 dB is actually 100 times, that's 10 to the power of 2, more powerful than 0 dB. And this will take some time for you to kind of understand and get used to, but every power of 10, every 10 degree jump in decibels is a power of 10 increase. So 10, if you go up 10 dBs, okay, it's 100 times, 100 times more intense or more powerful. Okay, makes sense? 20 times more powerful than dB. Nope, it doesn't make sense. Sorry, I got to change that to 10 here. So up 10 dB is 10 times more powerful. So 10 to 20, 20 to 30, so on. All right, take a look at the page 356 chart, and you'll kind of get an idea of the relative, sound intensities of different things. Okay, so your chart is not like this. You have some more details, but just generally for our notes here, 0, okay, that's the threshold of hearing, the softest sound a human can hear. A ticking watch is about 20 dB, pretty quiet, right? The rustling of leaves, about 30 decibels. A quiet library, 40. Normal conversation, between 55 and 65 decibels. A quiet library, like just the rustling of pages and people walking, maybe even some light whispering. So a vacuum, 60 to 65. A lawnmower, that's 60 to 85 maybe. A lawnmower, about 90 decibels. When we do sound, I do sound at church, and I'm part of the worship at church there. We have a decibel rating for each service that we kind of try to aim for. And some services are quieter, some services are louder. So the music at church where I play ranges from 85 decibels to 100, so in between there. It's usually an average of about 85 for the one service, and then 90 for the other service, and maybe up to 95 for the third. So that's about the sound. So if you've ever been to the app there, that's sort of where we are right there, about the sound of a lawnmower. Okay, hearing protection is required. Anything above 85 decibels. So if you come to my church, apparently you're supposed to be wearing hearing protection. But anyways, headphones, okay? Sometimes headphones can get really loud. You kind of have to be careful there. You pump it up. It can be up to 110 decibels. A jet taking off, 140 decibels, okay? So those jets that were passing in that video, it'll be pretty loud. And then instant hearing damage occurs at about, what is that? About 140. On your chart there, 160 is instant perforation of the eardrum. So that is enough energy. Your eardrum will vibrate so much that it'll just break apart. It won't be able to handle it. So that's not good. So when a jet is taking off, that sort of thing, you got to be very careful. And interestingly enough, a wind tunnel, if you are actually in a wind tunnel, those where they test for aerodynamics and they kind of send the smoke and it goes over the shape of the car, wind tunnel, where they test all that kind of stuff. If you were actually in there, super, super loud. That's similar to a rocket launching. So really, really loud. Anyways, that's some decibels, and so you have some relativity there of what the sounds are. Okay, so just to kind of complete this, here's some other things. You don't have to write this down here though, but this part you do. dB SPL, the decibel in reference to the sound pressure level, and that's really what we're talking about when we're talking about decibels, the sound pressure. dBm, dBV, don't write that stuff down. But this decibel here, it's the sound pressure level. And it's the common one we use for intensity of sound, so we don't really write the SPL, we just write dB. And perforate, perforate means that holes would appear, like it would actually break apart or it would split.